Welcome to Google Cloud AI Developer Relations Virtual Training. My name is Andrew Furlich, and I'm a staff member at Google Cloud AI Developer Relations. Today, we're going to cover part 10 of our Junior Data Science series, and it's the portion we call a part 2, or not part 2, session 2 of data pipelines. So, this is just an overview of what we're going to cover. Now, the data pipeline is actually part of what we call a larger pipeline, which is the end-to-end production pipeline. And in the last session and this session, we're just covering the data pipeline portion of that. And in the previous session, we covered data formats and storage and data feeding. In this second session, we'll cover data preprocessing and data augmentation. So let's just take a step back for a moment and look at a basic end-to-end production pipeline. Okay, so we start here with some method that you are warehousing your training data. This is the data you're going to use to train your models. And you have some method of feeding or drawing data from the warehouse and feeding it into the system that's training the model. And today, unlike the past, we don't train a single instance of the model. We're likely training multiple instances of the model, probably using different hyperparameters. For example, doing automatic hyperparameter optimization. And even with that, we generally will do, for every one of those, we may be doing some minor pre-training or instances of pre-training, such as warm up to get the weights, the initial weights in the model to what we call numerically stable before we take the instance of that model and then start doing hyperparameter tuning on it and so forth and so forth. But eventually we get to an instance that we're going to do full training on. Once that model is trained, we want to check if this is a better model than the last time we trained. Now, in today's world, we're doing continuous integration, continuous development. Okay, and that means that we have some kind of repository now, like equivalent to a source code repository, but now it's a model repository, and we're going to have versioning. And we're going to have some method of comparing the new one we just trained with the last good one that we had trained. And if it's not better, then of course we're going to repeat this cycle again. Otherwise, we're going to go ahead and version it and put it in our repo and then deploy. So we're covering in the data pipeline series really just this portion here. Okay, so let's talk about preprocessing. And I'm going to talk about it in sort of the TF2X perspective. So when TensorFlow 2.0 first came out, one of the recommendations was to move preprocessing into the graph. And we've discussed this in earlier sessions, so I'm not going to dive deep into the reasoning why. But when you move preprocessing into the graph, you can do this with what we call a prestem. Okay, now that's the approach I recommend, or actually, the approach I recommend is to make it independent of the model, so that your prestem can be plug and play, and interchangeable. Okay, so what that means is you could have a whole bunch of different prestems, and this is your normal model here, and the beginning of the model is your stem group, and you just attach these prestems to it for your specific preprocessing purpose. And again, these prestems could be used on other models, and so they're reusable. The only real requirement is the output of these prestems must match the input of the stem shape of your model. Okay. So yeah, I just kind of covered what were the prestem requirements for Prestem to be plug and play with existing models, whether they're trained or untrained. Again, I'll just reemphasize the output from the Prestem must match the input from the model, and the input shape for the Prestem must match the input source, whether it's for training or prediction. Now, that doesn't mean it has to be the same input source or input shape of your model. It just has to be the same input shape of your data source. Okay, so there are basically two types of prestems, or two categories they can fall into. One is where the prestem stays with the model after it's deployed for prediction. For example, the prestem does resizing and normalization of the input source. So during training, all the data coming in is resized to the correct shape for your model, and then the pixel data is normalized. Okay, during prediction, you have to do the same thing. Okay, so the prestem stays with the model. The other one is it's used during training, but after training, it is removed. That is, it's not used after deployment. You actually tear it off. An example of this would be using it to do image augmentation, like to learn translational and scale invariance during training. Sorry about the phone. Always a distraction doing stuff at home. Okay, so TensorFlow Keras 2.2 introduced some new layers for preprocessing, and we'll cover 3 of them in this section. One of them is rescaling, another one is resizing, and the third one is center crop. So in the next slide, I'm going to show a plug-and-play prestem that we can add to an existing model prior to training. Okay, so the way we'll first start off here with a tiny little model we'll make. We're going to create an untrained covenant. It's going to have 2 convolutional layers. The first one will be 32 filters. The second one, 32. And then we'll finally flatten it and have 10 categories. And you can see our input shape is 32 by 3. Probably sounds familiar. That's like a tiny covenant for CFAR 10. Okay, so to make a prestem that is plug and play, we use what's called the wrapper model approach. Okay, so what we're going to do here is we're going to create a new model, an empty model. We're going to call it a wrapper. And the first layer we're going to add is the rescaling layer. This is the one in the preprocessing library that does normalization. And I'm just going to tell it to divide every pixel by 255. Notice I'm specifying the input shape to my single layer prestem to match the CFAR 10, 32, 32, 3. The output shape from this rescaling layer is going to be the same as the input, so its output is going to be 32, 32, 3. And then the wrapper, I just add the entire other model as a single operation, as if it was just one layer. But because the output of this matches the input of this, they snap together. And now I just compile it. And just to show you here where to find these layers, they're not under TensorFlow Keras layers. They're currently under add-in .experimental .preprocessing. Okay. So let's make our model, our prestem, a little bit more flexible. Let's say we wanted to not just do the normalization with the rescaling, but we also want to resize the images. And let's say hypothetically, our model actually took an input source of 28 by 3. Okay, but our training data, okay, is 32 by 32, so we need to resize it. So we're going to use the preprocessing layer resizing that resizes these images to 28 by 28 and then do the normalization. So that's our prestem. Then we add in the model. Since this output is 28, 3, and we assume this model input is 28, 3, they just snap together. Okay. So how do you now tear it off? Okay, well, after the model is trained, we can remove it and use it for inference. So let's go back to the previous example here. And let's say downstream, we already have, during inference, after we've served the model and it's doing predictions, there's some other mechanism there that already does the pre-processing. It will already take an image and resize it to 2828, and it will already normalize it. So let's just say in this situation is redundant. So what we want to serve is we want to tear this off and serve that. Well, if you look, what layer does the underlying model start at? Well, this is layer 0, 1, 2. So we know it starts at layer 2. Okay, so really all we need to do is go to our wrapper model and reference it starting at layer 2, and that's our underlying model. And now I can use that model to do my prediction. Okay. We can also chain prestems together. Now, let's say we have one prestem we're going to use for training and remove it for inference, but we have a second one that's going to stay with the model both for training and for inference. And so for one example is the one that stays, let's say it does the normalization, okay? And let's say that the one that we're going to excuse me. Yeah. Okay, that we're going to tear off does a center crop. Okay, now the center crop here is a little bit different. Okay, what this one does, the way this one's defined, is that you specify a size, a crop size of the image. Okay, and let's say we're going to say our model takes 32 by 32 by 3. Okay, so that's what it's going to output, and it's going to center it and crop that out. Okay, and then the rest gets discarded. Now we want to train it. We're going to say on images of different shapes. Okay, that may not necessarily all be even of the same shape. So you probably may not have seen this before. I can actually specify in my input shape. I don't have to give it a specific shape like 32, 32 or 256, 256. I can go none, none. That means that feeding, I can feed it any image regardless of its height and width, as long as it's got 3 channels, of course. And then it'll automatically, regardless, cut that 32 by 32 out. Okay, so let's kind of back up here. So I create my first wrapper, the one I'm going to keep, right? I add my image preprocessing to it, and then I snap in the model. Ooh, actually, that's incorrect. Okay, no, that is correct. Is this line incorrect? Okay, and then I'm going to compile it. Okay, what this is supposed to have here is wrapper 1. Okay, then I create the outer wrapper. It's sequential. I'm going to add in my next prestem. I'm going to chain it. Okay, so it's on top, it's on the outer. It does the center cropping, and then I'm going to add the first wrapper. So that's a typo there, and then compile it. Okay, now I can train it. Okay. And then for evaluation, I want the underlying model. Well, this is layer 0. It's at the top. This is layer 1. So I can tear off the second wrapper, the auto wrapper, and keep the inner wrapper and model by referencing layer 1. Okay. Another way of creating a prestem is to make your own custom preprocessing. Okay, so if what you need to do currently isn't in the new Keras preprocessing layer, you can make your own. And all those layers themselves are subclass or inherited from the TF.Keras layer class. So you're just going to subclass this. And that layer class has 3 methods in it that you're going to need to override: the init for the initializer, the build, and the call methods. Okay, so init, of course, that's the initializer when you instantiate an object. So here what we're going to do is we're going to recreate the rescaling layer as a subclass. So I'm going to declare a class called rescaling, and I'm going to inherit from the Keras layer class. Okay, now the init has some what you call default or keyword parameters. One of them is the input shape. Okay, I'm leaving it unspecified at the moment, and optionally a name for that layer. Okay, and then I'm going to add a positional parameter. This is my custom parameter. I'm going to call it scale, and that's where you're going to pass in that number. Let's go back to an example that actually has it. See how scales right here? So that's how I just implemented that parameter. Okay, and presumably I'm then going to save the value of that scale. Okay, then build. Build is called when the thing is compiled. Okay, now if you're using the functional API, it is called when you actually say compile. Okay. Okay, when you are using the sequential API, it is incrementally called every time you add a layer. Okay, now also notice that it has repeats input shape. Again, it's a difference between the sequential API and the functional API. Okay. I don't remember which. I believe it's in the sequential API that, yeah, when you instantiate the layer, okay, you the top layer, you always add the input shape equal. So when you create that first layer in a sequential API, this is when the input shape is specified. Okay. But in the functional API, you refer to it as a tensor, okay, and then call the layer as if it was a function, passing in that tensor, which invokes the build command, and that's why input shape is here. Another important element of build is that it also is where you specify the kernel. So in the case of a convolutional layer, that's going to, let's say, is a 3x3, that's going to be that 3x3 matrix, and that's going to hold the weights, okay, or the initial weights. Here we have no kernel to learn, so nothing to backwards propagate through it. So we're going to set it to none. And then the all-important one is call. This is what gets called when the graph, your model, is executing, when data is being fed through, whether it is training or for inference, when it hits that layer. And by default, the arguments to it is inputs, and that is the batch that is coming through. That is a tensor, okay? And we're just going to then multiply that tensor by our scale factor. Because it's a tensor, that operation will get broadcasted to every pixel in that tensor or in that batch. Okay, and so the output of this is going to be the same as input, except every pixel is going to be divided by the scale value. In the case of 255, divided by 255. So I've just re-implemented the rescaling preprocessing layer. Okay, and we also need to add in this decoration at tf.function, and that just tells that during execution, this operation needs to be put on the graph. Okay, so now let's look at a different way of doing preprocessing. Let's do it, say, using TF extended or TFX. Now, TensorFlow extended is a end-to-end production pipeline. And in this section, we're going to cover only the data pipeline portion of TFX. So this is the TFX data pipeline portion. So outside of here, you have your data set, your data. And we'll go into each one of these in detail in a bit. Okay, but you have what's called example gen, statistics gen, schema gen, and example validator. And collectively, these four modules make up what's called the data validation library. And then you have the transform module, which makes up the transform library. So let's now go into each one of these one at a time. Okay, so example gen, its job is to ingest data from a data source. So it knows how to read it, whether it's a CSV file, a TF record, a big query. So that's what we're showing here in this diagram. Example 10, ingest data. Of course, it's going to be used for various things. Okay, so you can see it has two paths here. We'll cover in a moment each path. Okay, statistics 10 takes input from example gen. It's drawing data out of your data source, and it's analyzing the examples from the data set, and it's producing statistics on the data set distribution. Okay. The next thing in that chain is schema gen. Now, it takes as input the data set distribution outputted from a statistics gen, and it uses it to construct a data schema. So in the case of, let's say, not an image, but let's say you were doing, structured data, it would identifying and assigning the different columns of data feature types, for example. So let's go back to the picture. So here you are, right? Here's schema gen. It takes its input from statistics gen that's got the data set distribution that takes input from example gen that's feeding it examples, and on this end is drawing the examples from the specific data set. Okay. Then we have example validator. This is typically really used during training, okay, and serving. The assumption here is at times your model is going to see a sample or an example that was never part of this original chain of example gen, statistics gen, and schema gen. And its job is to look for examples that don't belong here, you could say. That is, there's some anomaly in it. Okay, so it's validating, yes, you match the schema. Okay, but if you don't match the schema, it would flag it. Okay, and then finally, transform. And this is what you would use during this is where you do your feature engineering, if you're doing structured data or data preprocessing and data augmentation, if you're doing, regardless whether you're in structured natural language processing or image data. Okay, so let's go back and look at that. Okay, so you can see transform is taking this data from example gen, okay, and how to pre-process that data. Okay, part of that information it uses to do that comes from schema gen, the schema of the data. Okay, so let's start looking at some source code here. Okay, so these components, actually is what they're called, not modules or packages, come from tf.component. So we're going to just import them all. Okay. Notice that with the extension of example gen, the name of the class is the same as the component, but we have a little exception here on example gen. There's more than one type of example gen dependent on the type of source. Okay, in our case is we want to draw data from disk, so we're going to import it. So we're going to bring in import example gen, but there are different ways we could be pulling it from there. So we're going to, from the utilities, we're going to pull in this one specific method called external input, and this method handles data that's in a TF record format. Also, okay, so that's the pipeline. Nothing happens. You connect this all up and nothing's happened. It's just a pipeline. You have to execute it or run it. So we need what's called a context to run it in. This is kind of similar to TF1 where you had a session and you then ran that session. It's comparable. You have this context, that's your session, and then you have to run it. Okay, so we need to create a context. In this case, I'm going to create an interactive context so you can watch it, you can interact with it and watch it happen step by step by step. And it's actually a good thing to do the first time you put together a pipeline, that you can actually debug what's happening inside of it in the interactive context. Okay, so step one is I have to create my context. Okay, All right. Then the next thing I need to do is I need to instantiate my example gen, and I'm going to need a helper function for my input. And that helper function is going to be this external input. And this is presumably the name of the file that I'm reading from, or directory, actually, that I'm going to read TF records from. Okay. And so that you could say is my connecting function. That's the thing that's going to connect example gen, how to read TF records off a disk. Okay. And then we have a context, so we can pass this component to that context and run it. And I'm not going to show you the output here from it, but it'll give you what's called artifacts. Okay. And in this case, the artifact would be, information about the input and information about the output. Okay. So the next thing I can do, okay, is I can add now to the pipeline statistics gen. And I want to back up here. When I ran example gen here, because I had nothing telling it to draw samples from it, yes, it poked and it made sure it could read it and so forth, but it didn't actually like draw all the data out. Nothing's asked it at this point to draw data out of it. Okay. Now I'm going to instantiate a copy of statistics gen, but it needs to be connected to something. And the parameter here is examples. Where am I going to get examples from? Well, you get it from the example gen we created, and from the outputs of all these generators are actually dictionaries. Okay, so you go to the output dictionary and use the keyword examples, and that's what we're connecting to. Okay, and what will happen is when you run statistics gen, it's going, think of it as kind of going backwards. Okay, I'm connected to the output of example gen for its examples. Okay, and I'm going to call it, and that's going to work backwards to example gen, and example gen is going to draw an example, and then push it forward through to statistics gen, and it's going to try and call example gen again to get an example, and it's going to just keep repeating that until it's read through all the data. And then it's going to generate statistics. So where are your statistics? Well, they're in the outputs of statistics gen under the dictionary key statistics. And like I said, everything is labeled, all these outputs are labeled as artifacts. So the distribution is going to be under artifacts 0. Okay, so let's move up. So schema gen component generates the schema from the data set statistics, right? Okay, let's go a little bit back here and look at our picture. So we're here now. We did this one, we then added this one. We're now going to add this guy here. Okay, so instantiate schema gen. Who is the input? The output of statistics gen. So we go to its output statistics. Run it. That's just going to work backwards and execute a pipeline. And when it's all done and it's gotten the statistics, it's going to generate a schema. Where is the schema? Well, it's going to be in the outputs in the keyword schemas under the artifacts. Okay, now we're ready for example validator. This component is a little different in that it needs 2 inputs. Go back to the diagram. It needs the schema and the statistics. So when we instantiate this, we're going to have to specify both these outputs. Go back and see that, and there we are. So we have 2 inputs, the statistics and the schema, and of course they're the outputs of the corresponding components. Instantiate it, now we can run it. Okay, and then the output of that is going to be in the key dictionary key anomalies under artifacts. Okay, so transform is kind of the last one we have to cover in this section. Okay, you can see in the pipeline it takes 2 inputs. One, the example is being drawn from your data set, and the schema. Okay, how to what's in the data. Okay, it also takes a third thing, and they call it module. And that is a Python file, excuse me, you wrote about how to preprocess the input. So this is a custom file that does the preprocessing. So the transform function itself doesn't have like operators or parameters where you say do this, do that, do that. Is you write it yourself. And then of course, now I can execute. All right. So that's our section on data preprocessing. So now we'll start on data augmentation. Okay, or in our case, image augmentation. Now, it has a variety of purposes, but at first, people looked at image augmentation as a means of extending or adding to an existing data set to have more images to train on, and by doing some kind of random transformations on those existing images. Today, we kind of look at it in a different way for more targeted purposes. Okay, and so our approach is different depending on the targeted purpose. So we might be training the model to learn invariance. We might be training the model to do what we call essential feature learning, or we may trying to get the model to generalize to data drift. If you're not familiar with data drift, is that the data set you train on has a distribution in the population. You might recall from the data distribution part of this series, that would be a sampling population. But when you deploy the model, the images it sees may be close to that distribution, but a little bit outside of it. That is, it drifts. It's a slightly different distribution than what you trained on. And ideally, you would like your model to be able to generalize to these data drifts that are going to occur when the model is deployed in the real world. Okay, so let's start with invariance. So we're going to train the model to be what we call translational scale and viewpoint invariant. Okay, and what do those words mean if you're not familiar with them? Well, translational invariance just means we want to be able to recognize the object regardless of where it is in the picture, whether it's in the center, whether it's left, whether it's right, whether it's top, bottom, or anywhere in between. Okay. Scale just means we want to recognize the object regardless of how big or small it is in the image. So it could take up the whole image or just a small portion of the image. And then viewport invariant is your perspective. You could say the angle that you're looking at it. Is it straight on? Is it a little bit overhead? Is it from the sides? Is it rotated a little bit? Etc. That's your viewport, and we want to be viewport invariant. An image augmentation is really good for training a model to be translational scale and viewpoint invariant. So that's a targeted purposes. And if you look at ablation studies and research papers, there's a common set that pretty much all of them use. Okay, and those are the random center crop, random flip, random rotation, and random shift. And we'll cover each one of those. Okay, so a crop is when we take a portion of the image. We already talked about it earlier in the center crop preprocessing example. This is different. This is a random crop. And it's going to be of a rectangular shape. And this type of transformation contributes to the model learning scale invariance. Okay, so, and I'll show that here in a minute. So it generally starts with a center crop, and it's going to randomly pick a subset size of the image, but usually it's only a small portion of the image is dropped off. Okay, meaning they're not tiny little crops. There's still most of the image, but just how much you're dropping off is randomly chosen, hence the word random. So you get a slightly smaller image here, right? The part of it's been cropped out. And then we resize it back to the original shape. That's what a random crop does. So that's the example here. Here's an example of this cat. It's the original. It's randomly cropped and resized back to the same shape of the original, but it's been cropped. And that is how we train it for scale invariance, or one method we use to contribute to training for scale invariance. A random flip is when we flip the image on either the horizontal or the vertical axis. So, flip it this way or this way, okay? And this contributes to what we call the viewport invariance, okay? And it also helps contributing to learning essential features of the object. So think about the horse, being able to recognize. It's not just being able to recognize the horse if the head's on this side of the picture, or flip it around, it's on this side. But by flipping these things around, it helps the model focus on the things that are the horse and not on the things that are on the background. Okay. Random rotation. And I'm going to we usually do this with some form of chaining. Okay. But let's start with the rotation. Now, what it means is that we're going to rotate the image along the center point. And again, this one contributes to viewport invariance, just kind of similar to the flip. And the common practice is to pick a random amount in a range of plus or minus 90 degrees. And that's usually considered sufficient. And we generally combine it with a random flip. Okay. Oh, excuse me, with a random center crop, and another typo in the slide. Okay, so here's an example of the image where we've done a random rotation, and we're going to fit it into a box so we don't crop anything out. And then we're going to randomly crop the randomly rotated image and then resize it back to the correct shape for the training. Okay. All right. And then there's random shift. Well, random shift is when we shift the image vertically or horizontally. So we shift it a little bit like this or a little bit like this. And when we shift it, obviously, some pixels are going to drop off. Okay. And this type of transformation contributes to training the model for translational invariance, regardless of where it is in the image. So if we're shifting horizontally, we're going to be dropping pixels off either on the left side or on the right side. And then we're going to replace them with the same number of pixels, or they're typically black pixels. Okay, why do we choose black? Well, the value of black pixel is 0, which means no signal, because 0 in a matrix multiply operation outputs 0. When we are shifting vertically, now they're dropping off at the top or bottom. And the general rule of thumb is we don't want to shift too much off. Okay, we usually pick a random amount within plus or minus 20%. Okay, so you kind of got the idea of the basic types of these transformations. Okay, so I'm going to show you how to implement them using tf.data. Okay, so image translations can be added to a tf.data.Dataset pipeline using the map method. In this case, what we're going to do is we're going to create a Python function that's going to use Tensorflow transform operations to do a transformation. Okay, so our function here, we're going to call it flip. Its input is going to be fed. It's going to get one example at a time. An example is a combination when it's coming from the training data. It's the actual image and the corresponding label. Those are the two functions. We're going to want to do some transformations here. So using tf.image module, I'm going to call the random flip left or right to randomly flip it left or right, passing it in the image. That's my first transform. Then I'm going to pass that guy to another one right here that's going to randomly flip it up or down. Okay, now remember that in random, it doesn't mean we actually always do it. Not doing it is one of the random choices. So one of the possible outcomes of these two chain transformations is the original image. Okay. And then finally, we want to return from this the transform image and the label. So that corresponds to the input is image label. Now it's the transform image label is the output. Okay, so we're going to instantiate a tf.data.Dataset. We're going to use the from tensor slices method to bring in a data set that is in NumPy format. So you can assume, let's say, pretend this is CFAR 10 data that got read into memory. Okay. And then now that we got a data set for this data, we're going to apply the map method. And we're going to tell it that every time you draw an example from this data set, you run that example through this method. So this isn't being executed at this moment. It's executed when you're drawing data through it. So when you're training and you're drawing a batch, right? So you get the batch, and then in every example in that batch will be mapped through this function. Okay. This just kind of shows you how you can chain together different transformation functions. So let's add in a second one. I'm going to call it crop. Obviously, input is an image and a label pair. And this is just my implementation specification. In random crop in the tf.image package, you specify the shape, and it just randomly selects, it's not the center, where in the image to do the crop. So I have to come up with a shape. That's what I've done here. It's just going to be 80% of the original image. Okay. And again, it's going to output the transform and image and the label. Now, when I got a TF data set, I can just chain together these two transformations. So I'm going to first map the flip, and then I'm going to map the crop. So when this item is actually pulled from this example, pulled from the data set, it will first go through the random flips, and whatever comes out of the random flip transformation will then be the input to the random crop transformation. Okay. So here, we're just going to go back and do a little revisiting of the TF.Keras Prestems. Okay. The last time we were there, we looked at ones only for translational invariance. For invariance and not for augmentation. Okay. And so we have other ones here that can support other things. Like our random crop or actually I said that wrong. Sorry, back up. Okay, so we're just doing a little deeper dive. Yes, all of these are used. The other ones were being used for pre-processing. This set that we're going to show here are for doing things like invariance, like translational scale and viewport invariance. Okay, so one of them is random flip. Okay, and another one is random translation. So random flip obviously is doing a random flip like this or like this. And random translation is actually the shift, left, right, up, down. And here we're just going to implement these as a prestem. Okay, so that means we're going to have to create a wrapper model, an empty wrapper model. We add in our pre-processing layers and then snap in the model. And again, I see another typo. I have not specified the input shape here. Okay. I want to thank you for watching. We actually have one more section in our Jupyter Data Science series, and that is that whole back half of the end-to-end pipeline. We just refer to it as the training pipeline portion of our Jupyter Data Science series.